Alright, so as you see my screen, the topic for today is open shortest path first. Okay. In short form, we call it as OSPF. Very popular protocol, routing protocol from your certification as well as from your production as well as from your interview point of view. This is something which you will be dealing most of the time. Okay. I'm not sure if you guys are dealing up with EIGRP, but OSPF is one such protocol which you will be seeing it in your day-to-day activities. Okay, so yes, as we know, these are routing protocols. Okay, so basically inside your LAN segment, to give the reachability between the distribution layer towards your core layer or the ISP. Okay, you need to have some routing protocol which are acting as a dynamic routing protocol, which can take those user packet and forward to ISP. Okay, for ISP, the between ISP and the core we have protocol like BGP, but in case of LAN segment we need some dynamic routing protocol which can do the forwarding. Okay, so as we know, we learned about static routing. The drawback about static is we have to manually define, and then we covered of EIGRP. EIGRP is a good protocol. Okay, it's fast convergence, it's simpler to configure. Now the thing is, we need, let's say we have multiple router, let's say we have thousands of routers. Okay, we need to do a lot of advanced thing inside OSPF. We need to manipulate, we need to scale the network topology. Let's say just a simple example. Let's say I have couple of routers. Okay, might be in thousand of number. In case of EIGRP, I have to enable this EIGRP on each one of them. Okay, if there is a small change on one of them, that update would be taken up to all other routers. Okay, over on update packet. So these are some challenges in the case of EIGRP. In case of OSPF, what I can do is I can bring some concept of area. Okay, so what is that going to do is, let's say I have multiple router. Okay, and one of the router is advertising a new route, or it is deleting a network. So basically that will be distributed to each and every router. Okay, so in case of OSPF, what I can do is I can put a logical boundaries. Okay, I can say this is a part of area 1. I can call this as area 0. I can call this as area 2. So now what happens if there is a change over on this router, those update will be only limited within this boundary. So that makes it more advanced. Okay, we can scale the whole topology. We can scale around thousands of routers in a LAN segment into couple of areas. I can put like 20-30 routers in one area, so that the update packets, the query packets are within the boundary itself. Okay, so we can do much more thing in OSPF. So we will start up with one after one. Okay, that was a quick introduction about OSPF versus EIGRP. As we move on, I'll keep on telling the differences. Okay, so let's start from point number 1. There is no hop count limitation, as we saw in the case of RIP. Okay, as well as in EIGRP, if you remember, it supports 100 hop counts, but yes, we can extend it to 255. In the case of OSPF, there is no concept of hop counts. Okay, OSPF doesn't count hops. It's all purely metric. Metric is nothing but the cost in case of OSPF. Rapid convergence, the reason is, as we checked out in EIGRP, it keeps primary link inside routing table. Agree? and the feasible successor in the topology table. It was maintaining two different tables. One is routing table, one is topology table. Similar way, even OSPF is going to maintain its own primary table. So primary table will have the primary route, and the backup route will be placed in the topology table. Now that's make it more rapid convergence. Whereas in RIP, there is no separate table. It just have one single routing table. So it cannot accumulate, or it cannot make a note of backup. So once a link fails, it has to recalculate. It has to find out the next path, and meanwhile it is going to take like 90 to 120 seconds, which is equals to like 3 minutes or 4 minutes, right? In case of RIP. Whereas in EIGRP and OSPF, since it's maintaining a dedicated topology table, the convergence is very easy. As soon as this goes down, as soon as the concept of hello timer and hold timer get expired, okay, as soon as hold timer expires, like let's say 10 seconds, a backup link will be now acting as a primary link. Okay, so that's why these protocol like EIGRP and OSPF, we call it as rapid convergence. Okay, so we checked out one more thing in EIGRP. By default, EIGRP will support class full. Okay, so that means, let's say if I'm advertising 172.16.1.0/24. So by default, what is it going to consider is 172.16.0.0/16, because it's a classful nature. Okay, so class A will have /8 by default. Class B is going to have class 16, and class C will have /24. This is a classful in nature. Now what is classless? So let's say if I have 10.1.1.0/24. Now this is not a example for class A. Okay, it's a class C example now. The reason, because of the subnet mask. Okay, similar way, let's say I have 192.168.1.0/24. Let's say I have 172.16.1.0/24. Now these are all class C example. Okay, as well as what I can do now is, let's say I take up one whole network. Okay, that, let me write it here, 192.168.1.0/24. Now let's say I'm dividing this, or I'm splitting up this whole network of 254 valid IPs into smaller blocks. Okay, as per my requirement. Let's say I need one block to have 10 hosts. So I'm going to make use of this 192.168.1.0 slash let's say 28, which can accumulate so many hosts. Now let's say I have another requirement where I need 30 hosts. Now same thing, let's say 192.168.1.20/26 is going to give me 30 hosts. Similar way, let's say I have 50 host requirement. I'm still making use of the same parent network. Okay, but I'm just changing on. Okay, if you see, the IP is getting changed on. I had 0 with /28, I have 20 with 26, I have now 70 with, let's say 23. Okay, not 23, let's say 25. So this way I just divided a whole single network into multiple different network. Okay, now they are called as VLSM, variable length subnet mask. Now there is one more thing called as fixed length subnetting mask. That's a scenario when the parent profile is divided into equal components. Let's say the whole network will be divided into each 30 blocks. Okay, so I need to find one network to this, another network to this, another to this. Now the drawback of FLSM is there will be lot of wastage. Okay, not weightage, there will be lot of wastage, in the sense I only wanted 5 valid IPs, but due to FLSM I have to make a block size of 30. Now that's a drawback. Okay, I'm wasting 15 IPs here. Whereas in VLSM, if I need only 5 users, I can make sure that I create a smaller block. Okay, so this is something which you have already gone through in CCNA, just revising few things if you just to recall the things. Okay, so open shortest path first, or OSPF, is going to support VLSM, that is a whole single network. Okay, let's say if I break it into multiple variable length subnetting mask, let's say /26 /28 slash, now this is supported in VLSM. Okay, that's whole point here. OSPF is going to support password authentication. Okay, so it's going to support MD5. It's going to by default have the plain text mechanism. Okay, advanced path selection capabilities. So that's something like, let's say I have a primary link. Okay, if this goes down, then I have the backup link with me. Okay, as well as I can have lot of options, or I can have lot of enhancement, like I can have route summarization. Agree? Something we learned in EIGRP also. I can tag external routes. Okay, that means, let's say this is a OSPF network. So my company just overtake another smaller company which is having EIGRP. Now let's say the user from this company wants to send a file across to that smaller company which runs on EIGRP. Now I can redistribute. Okay, so this is called as redistribution. And now this external routes which are learned inside OSPF, we can tag them. Okay, so those are few advanced path selection capabilities that we will discuss in OSPF. Okay, tagging the external route, that's something which I told. If there is a route which is coming from static routing or EIGRP, so we can tag them. Okay, we can tag them to identify, also to play around with the path. We can say that this tag should be considered first rather than the next tag. Okay, so tag has its own plus and minus. We will discuss about tagging. Better use of bandwidth via multicast and periodic routing updates. Okay, so OSPF is a multicast routing. Okay, so all the advertisement will be happening over on multicast. In case of any changes, it's a periodic routing update. Okay, any changes, any modification will not happen instantly. Okay, it's a periodic routing updates. As soon as there is update, it will do the periodic update, or else if there is a new change or new addition, then it will be instant. Okay, so both are available in case of OSPF. So a whole network can be divided into logical concept that's called as areas, which we had a overview few minutes back. Okay, so whole environment of thousands of routers, I can just virtually make some areas and I can just place them. Okay, so we'll talk about areas, the areas concept and areas policies, all those things. Okay, so as I told, OSPF is a multicast address. All your reliable routing update happens over on multicast. Okay, OSPF will support equal cost over multiple path. Okay, so there is no unequal routing as we saw in case of EIGRP. OSPF is going to support equal load cost balancing. Okay, yes, MD5, and we have the plain text which is over here. Okay, in the case of OSPF, there is no split horizon issues, whereas in case of EIGRP, we saw that there can be split horizon issues. Split horizon is a concept to avoid looping. Okay, to avoid looping in the L3 environment. So we made use of split horizon over on the EIGRP to avoid such looping. In the case of open shortest path first, we don't have to take care of it, because OSPF is built in such a way that there is very less, or there is 0% of split horizon issues in case of OSPF, because it's going to document all the link information, okay, all the link in the network. So let's say I have something in this format, okay. So when I have OSPF, what happens is, once they form the neighborship, once the links are advertised, each router will know each and every other links, okay. Let's say this router R1, at the end of all neighborship, it's having 50 link in its database. Now this same link information will also be present over on this. It will also be present on this. It will also be present on this. Okay. The whole links will be advertised. All the, or I can say in very short term, that each one of the router participating under OSPF routing protocol, each router will know each and every links. Okay. So links are nothing but the network, what I'm trying to say. Whereas in the case of EIGRP, it's little different. So let's say in the case of EIGRP, from the point of R1, it will only know who is its neighbor. That's all. It will not know what is the link advertised or what is the link associated with R4. That's where your split horizon occurs. Okay. Or looping happens. Looping, what is looping? Whenever you're trying to send some packet to the neighbor might send back one of the copy to R1. Okay, now there is something called as looping happening. Okay, it's because R1 doesn't know who is next after its neighbor. R1 only have visibility to its neighbor only. Okay, from the point of R2 and R3, even these router will have visibility to its directly connected neighbors. Now, where is this neighbor connected? On what links are those neighbor connected? These individual router will never know. But in the case of OSPF, the whole links will be equally, or there will be complete consistency. Okay, all the router will know who is connected to whom. Okay, and what is the best path to be selected. So there is no split horizon issues in the case of OSPF. And as we know, OSPF is an example of link state. Okay, why do I call link? Link is nothing but network. Okay, so in the case of networking, let's say I have this router where I have enabled OSPF. Now this router will have multiple networks. Let's say this is connecting with some router, this is connecting to some router, let's say this is to some router, let's say this is connecting to some switch, and switch is connecting to some users. Okay, so on examples. Now this individual networks, okay, are actually called as link. In networking, links are nothing but these networks, so don't get confused. So when I say if this OSPF router know 50 links, that is nothing but 50 networks. Okay, so link is nothing but network. In OSPF or in networking, links are nothing but the actually it's a network. Okay, so they are link state dynamic routing protocol. So at the end, the routers are going to know each and every network in the topology. Okay, they use an algorithm which is called as shortest path first, SPF algorithm. It's a IP protocol. Okay, OSPF follow IP protocol type, and this is the IP protocol. They are neither TCP, they are neither UDP. Okay, they are neither TCP, neither UDP. They are a IP protocol which recognize IP number 89. What is the administrative distance of OSPF? It is 110. What is administrative distance? Is trustfulness, okay, or trustness of that routing protocol. So what is AD of EIGRP? It's 90. Okay, what is the AD of static route? It's 1. What is the AD of OSPF? It's 110. Okay, what about trip? It's 120. So this is how you should remember the different AD values. It's a classless routing protocol, and OSPF calculates or find out the best routing on basis of cost value. Okay. So in case of OSPF, cost value is very, the formula for cost is very simple. It's just reference bandwidth divided by bandwidth of interface. Okay. So it's directly proportional to the bandwidth of interface. Whereas in the case of EIGRP, it was dependent on bandwidth and delay. Okay. But in fact, the longest formula was dependent on multiple things like load, you had reliability, you had MTU. Okay. But when you just make use of those constant k values and you just have the shorter form of the formula, it's directly on bandwidth and delay. Okay. But in the case of OSPF, I don't make use of any constant values. It's straightforward, reference bandwidth by bandwidth of the interface, and I am going to get the cost value, and that's how I find out what is the shortest way to reach my destination. Now there are two multicast IP in the case of OSPF. One is 2240.0.5 and one is 224.0.0.6. Now this might be little confusing. Okay. So let's say I have multiple routers and they're forming the initial neighborship. Okay. So they are going to send hello packets to each router. Now that's happening on 2240.0.5. Okay. The initial neighborship formation will happen on this multicast IP. Now where is 2240.0.6 is used? So that's used. Let's say I have a switch. Okay. And all my routers are connected to this switch. Now this is an example of multi-access or multi-broadcast. Okay. So this kind of topology where I have multiple networks connected to a switch, we call it as multi-access. So let's say in this scenario, one of the network 1.1.1.1 got flapped or went down. Now what is this router going to do? Router is going to send that information to the switch. Okay. Switch, as we know, switch is a broadcast in nature. So what is switch going to do? That information that it just received, it's going to broadcast to every other router. Okay, in a broadcast nature. Now each router will get that update. The routers will synchronize and they will send acknowledgement packet. Okay. So you can expect one more copy of acknowledgement, and now this acknowledgement is again broadcasted to every other. Okay. So let's say the acknowledgement that is received here will be broadcasted. The acknowledgement that was received here, that will be brought. So basically you can expect the more number of routers you have in multi-access, the broadcast will keep on increasing. Okay. So in such scenarios, what we normally see in the case of OSPF is election of DR and BDR, designated router and backup designated router. Now let's say in this scenario, this was elected as DR and this was elected as BDR. Okay. So how is this going to help us? How is this DR and BDR are going to help us? So let's say now this router who knows that there is a BDR and DR, now instead of sending to the switch in a open broadcast, which is this MAC address. Okay. So what is the MAC address? What is the destination MAC address of a broadcast packet? It will be all F. And when switch receives some packet which is broadcast in nature with this destination MAC address, so it will just flood it to every possible network. Okay. So now in this case, when I have BDR and DR, now since this router know who is DR and BDR, it's going to send a multicast packet over on this address. Okay, that is 224.0.0.6. Now here is where your DR and BDR are listening. Okay, rest of routers will not listen on this. All your other routers will not listen. It's only your DR and BDR which will recognize this special multicast IP. Okay, so why do we use the second multicast IP? It's used in the case of multi-access network when there is a addition of new network or there is a deletion of any new network. Now that routing update will be sent on this multicast address. Rest are going to ignore it. They are not going to consider, they are not going to send acknowledgement. So you can just eliminate those two additional steps. Okay, there will be no synchronization, neither there will be a acknowledgement receipt sent. Okay, so you can see you are trying to reduce the overhead on this switch on the multi-access networks. Okay, so this packet will reach to DR and BDR. They will update their database and then they will share their updated database to other router, and now that's over on this multicast address. Okay, so in the case of OSPF, since we are dealing with a large number of routers, thousands of routers, 2000 of routers, that's why we see two multicast IP. One multicast IP, the first one for initial hello and neighborship formation. The next one is for special purpose, like especially in the case of multi-access network. Okay, so that's why we see this two things. Regarding the timer, it's 10 and 40. In the case of OSPF, it's always into 4. Okay, your whole timer will be into 4. So now that's going to be 40. Whereas in the case of EIGRP, it was 5 and 15, which is nothing but into 3. Okay, your hello was 5, hold was 15. But in the case of OSPF, it's 10 and 40 by default. Yes, it supports VLSM, it supports summarization. Okay, one more change in case of OSPF is that it's going to make use of wildcard mask. Okay, now what is wildcard mask? So let's say I have a subnet mask of 255, 255, 255, 255. Okay, how do I find wildcard mask of this? Just by subtracting 255. Okay, so you just need to subtract by 255, and that's how you get a wildcard mask. So in this case, it's going to be 0.0.0. Okay, let's say I have a subnet mask, class C subnet mask, which is 255, 255, 255 and 0. Now if someone asks you to calculate the wildcard mask, you just subtract with minus 255. Now that's 0. If you subtract with 255, that's again 0. If you subtract with minus 255, it's going to be 0. Now again, if you subtract with 255, don't say it's minus 255, because the mask or a subnet mask or wildcard mask, they are never a negative number. Okay, so you get 255 in this scenario. So let's say if you just re-bring to the subnet mask, so just add 255. So you will get 255, 255, 255, and okay, so basically you can subtract so that you get easy way to find the subnet mask. Okay, if you subtract with 255, it's going to be 0. So that's how subnet and wildcard mask are being calculated. There's the same thing. It's the way OSPF configuration is done. Okay, so in the case of OSPF configuration over here, okay, this step. So I go to the CLI of my router. I go to configuration mode. I will type router OSPF process ID. I will type network command. I'll say 1.1.1.1. Now, instead of subnet mask, I will say wildcard mask. Okay. So the network command will not be with subnet mask, it will be wildcard mask. That's why I gave you some easy example how do we find wildcard mask, and then you will type area 0 or whatever. Okay, so this is how we calculate or we configure OSPF. Okay, so same thing about the MD5, the authentication. So it's going to support MD5 and clear text. OSPF protocol supports summarization at ABR's router. Now for someone who is listening ABR for the first time, let me tell you, since we are reading about different areas, so you will read about multiple terminologies. Okay, terminology in the sense, let's say I have area 0. Okay, and within this area I have multiple routers. Now let's say I have one more area, which is area 1. Now this will have some more routers. Okay, let's say I have one more area 2, and let's say it's having some more routers, and I have a external routing. Let's say I have EIGRP, which has its own router. Okay, so in the case of OSPF, we will call, or we will have multiple terminology. Let's say the router within the area 0 will be called as internal routers. Okay, they will be called as internal router. Now the router which is over here, which is a part of area 0 as well as part of area 1, now they are called as ABR. Okay, ABR. Now that's nothing but area border router. Okay, it's called as ABR, the area which is sharing two different areas. Now let's say I have a router here which is sharing with area 0 and area 2. Now that's called as ABR. Now let's say I have one more router here which is sharing with area 2 and area 1. Now that's called as ABR. Now these are all ABR routers, area border routers. Now let's say I have one more router which is sharing with OSPF. At the same time, it's sharing with the EIGRP. Now this router will be called as ASBR. Okay, autonomous border router, because it's sharing between two different routing protocol, OSPF on one side, EIGRP on the other side. It doesn't matter on the other side if it's EIGRP, it could be BGP also, or it could be RIP also, or it could be static route, it could be anything other than OSPF. So any router which is sharing between two different protocol, one side OSPF and on another side you have any different routing protocol, you call such router as ASBR. Okay, and regarding this point, as we know, what is summarization? What is summarization? If you remember, instead of advertising individual networks, okay, let's say I have 22, 192, 168, 10.0. Okay, so let me take some other example. So let's say I have 172.16.23.0/24. I have 172.16.30.0/24. I have 172.16.34.0/24. 172.16.50.0/24. Now, when you enable summarization, so basically what you are doing over here is you will summarize this to a wide network. Okay, now this network will consist of all this. Okay, so basically how okay, so looks like I'm all right now. Okay, fine. So yeah, so as I was talking about ABR, it's where the summarization will happen. Okay, in short form, let's say I have multiple areas, area 0, area 1 and area 2. Now let's say within this area I have close to 20 networks. Okay, similar example, 172.23.0, 24.0, 25.0. Now when we are advertising those networks to area 1 or area 2, why should I take the burden of advertising individual network? Can't I do a summarization and just advertise it, right? So that would be much more practical scenarios, right? Instead of advertising each network, if I summarize them. Okay, so while summarizing, which is that router which will help me? It's your ABR router. Okay, so my area border router will help me in the case of summarization. Similar way over here, it's your ABR router that's going to summarize the route. So that's the point which I mentioned here. OSPF protocol supports the summarization at ABR routers only. There will be no further summarization. It will be happening only across ABR, which is shared between two different areas. Okay, now this is a drawback of OSPF. It requires more memory and CPU processing to run. But why do you think OSPF will take lot of CPU and lot of memory? Because it's going to keep a record of every link. There is two changes happening. One is periodic changes. So let's say every 30 minutes there will be a update packet sent. Even though there is no change or there is a change, there will be one periodic update. As well as you will also have instant update. That's when you have some reconvergence or there is some deletion, addition, there will be instant. So basically all these are contributing for high memory and CPU. Okay, so that's why OSPF will consume more memory and CPU. But we have the concept of area to fix this. Okay, area concept is introduced to fix this or to minimize the overhead, but it cannot bring something what EIGRP is into. Okay, EIGRP on other side is very lightweight program and also it's very fastest program, but it has its own drawback. It can lead to looping because it doesn't know who is connected to its neighbor, right? Whereas in OSPF, split horizon or there will be no looping, but you will face all these other issues like processing issues or memory issues. Okay, but yes, to minimize those things, you have something called area where you can place like 5 to 20 routers in one area, so that whatever happens which remains only within this area and not taken back to or taken out to different areas. Okay, now regarding the area, area 0 is a backbone area. Okay, so let's say your LAN, local area network, have multiple routers, so you can just divide in such a way that all other areas are connected to area 0. You can have any areas. Okay, you can have 1, you can have area 40, you can have area 200, you can have area 300, whatever it is. Okay, but make sure those areas are connected to area 0. Now how do you connect? Just keeping one router. Okay, the router which is sharing two different areas, and what do we call such routers? ABR, area border router. Okay, so area 0 is also called as backbone router in case of OSPF. OSPF have neighbor table, topology table and routing table, very similar to EIGRP. OSPF packet are only sent to neighbors of own area. Okay, so when they are forming initial neighborship, the hello packets are shared only with respective to their own areas. Okay, so the routers over here will not send the hello packet to different areas. Okay, they just form the neighborship among themselves. That's what this point says. They are going to support both IPv4, IPv6. Load balancing is equal cost. Okay, they will trigger updates for fast convergence. OSPF will send update, so the update packet will be sent over on this sequence number. The sequence number will end over here and they will start once again. Okay, so this is in the case of update packet. So let's say when one of the router okay, so let's say one of the router it just detect one of the network went down. Now that has to be informed. Agree? So that's about the sequence number. So it's going to send an update packet with the sequence number, and the sequence will end with this and it will start again. The sequence number will be incremented by 1. So basically the sequence will be getting incremented by 1, and that's how you keep a track of each sequence. So let's say if the sequence were split into 10 parts, let's say this whole information was of 5 MB. Now you cannot send 5 MB in one single update. So you have to split multiple updates. So once this update go and reach to the destination, now how do you combine them? So there should be some sequence number for every update, right? So in simple shortest form, so let's say this was the update packet, OSPF update packet, which was 5 MB size. Okay. So I cannot send 5 MB of update packet in one single packet. So what I need to do is I need to send it part by part. So first this part will be taken to different routers. Okay. Now this part will have some sequence number. Now let's say the next is this part, which will be taken up with the sequence number. And then there will be another part which will be taken up with another sequence number. So on the receiving side, all this part by part packet will now form a single update packet, okay, which is 5 MB, and now that will be recognized by the OSPF router. So that's where you see the sequence number. This is again CCNA topic. If you know TCP windowing or TCP sliding, there is where these topics come, where you send individual packets with header. Okay, so that's windowing and sliding topic in the TCP concepts. Okay. Okay, and OSPF protocol is more complex. Fine. So that's again something which we are aware of it. Okay. So let's go to next topic, that's regarding to the packet type. Now these are very important thing in case of OSPF. OSPF is lot of theoretical topics. So you will come across multiple theoretical topics here. Okay, so before explaining this topic, I will describe one more step and then I will come over here. Okay. Okay. So that's with respect to neighborship. So let me tell you what happens in the case of OSPF. So when you have OSPF running on your routing protocol, one second, is there something which okay, so I guess it's not for me, so I'll just go back to the topic. Okay, fine. So in the case of OSPF, the 3 steps happen. One is they form the neighborship, they will update the database, and they'll pick the best routing and will be put up in the routing table. Okay, 3 steps in the case of OSPF: neighborship, the database synchronization, and then the best route put up in the routing table. Okay, so we need to understand first how is neighbor formed. In the case of EIGRP ignored every possibilities in this case of hello packets. Okay, let's say in the case of EIGRP, even in the case of EIGRP, it took these 3 steps. That is, it formed the neighborship. There was no database synchronization. It only exchanged the routes between neighbors, and the best one was put up in the routing table. But even the first step in the case of EIGRP was pretty simple, because in the case of EIGRP neighbor state, they are going to ignore everything, ignore the hello and hold timer mismatch. Okay, There is nothing much over here which can bring the neighborship down. But in the case of OSPF, it's very sensitive. Okay, there are a lot of factors which can bring neighborship down. So that's what something we will see first. Okay, what are the components that will bring neighborship down? But before that, let's see how neighborship are formed. Okay, so OSPF neighbor shares the common OSPF enabled network. The router discovers a hello packet will be shared. The adjacent OSPF neighbor is OSPF neighbor that shared the synchronization. Okay, something which you guys go across. Okay, I'll tell you the 7 steps here in the case of OSPF. So let me make use of notepad here. Okay, so there are 7 steps. OSPF, 7 states to form neighborship. Okay, so the first step or the first state is called down state, init state, two-way, extract, exchange, loading, and full. Okay, so these are the 7 steps, and then they form neighbors, or I can call it as adjacency. Okay, so what happens? So let's say, to just brief this, I'll just take 2 routers which are connected straight, or a point to point setup. So I call this as router 1, I call this as router 2. So let's say in the first step, when the OSPF process is not enabled. Now let's say I just bring on the router OSPF process. Okay, so as soon as I bring router OSPF process, what is going to happen? They are going to send a hello packet, a multicast hello packet over on this multicast address. Now this hello packet consists of varieties. Okay, it's going to consist of router ID and other factors like hello components, hold timer, authentication, area type, area ID, and what else? 1, 2, 3, 4. So what else do it contain? It also contains subnet mask. So these are the content of the hello packet. Now let's say once you have enabled OSPF, now it goes to init state. Init state is when the hello packet is sent. It says that my router ID is 1.1.1. Now just don't worry about router ID. I'll tell you what is it. So it's just a IP address. Okay. So R1 is sending a hello packet with all this component within this hello packet, with router ID being 1.1.1 and all other components. Okay, is being sent to R2. Now that's a init state. Init state is when the router is sending a hello packet. Okay, it doesn't know on the other side there is someone listening to this packet. It is just sending its packet. Okay, now what happens is R2 received something coming in from somewhere, and the packet reads out to be 1.1.1. Now what R2 is going to do is R2 is going to send another hello packet, now in unicast in nature. Okay, because it knows there is some packet coming to be with 1.1.1.1 within it. Okay, so now it says my packet is 2.2.2.2. I am receiving something from R1 which is 1.1.1, and these are my parameters. Okay, it's going to share its own parameter, that I have this timer, I have this authentication, I have the area type, I have the area ID, I have the subnet mask. Now that's a unicast in nature. Okay, whereas the first one was multicast in nature. Now what happens, as soon as router 2 as soon as the router 1 see that there is a hello packet received onto this router, okay, with its own router ID. Okay. Now what is it going to happen, or what is router 1 going to say? So let's say when the hello packet, which had R2, R1 and all the component which arrived here, now R1 is going to be put up under two-way state. Okay. Now that's called as two-way state. Now two-way state is when R1 knows there is R2 and it has some parameter within it. Okay. So they form neighborship. They check the two eligibility. They are going to compare the they are going to compare these components. Okay. They must be matching up. So let's say hello and hold timer is 10 and 40. So you must have 10 and 40 on the other side. Let's say you don't have that. You have 20 and 80. Now they will not form neighborship. Okay. So you must have a unique or a consistency. The parameter should have be same. Only then they form neighborship. So when they form neighborship, we call it as two-way. Okay. So two-way state is called as neighborship. Okay. Now what happens? Even your R2 is going to send the packet with R1 and R2 ID. It's R2 is recognizing that. It's also forming in two-way state. Okay. They both are both are in two-way state now. They know who is connected to me, what is their parameter, and similar way R1 knows that there is R2 and it's know its own parameter, and they form neighborship. So I can say I can write over here they have formed neighborship. Now don't get confused. Neighborship is just one state in out of 7 steps. Okay. Now what are other things happening here? Okay. Or is there something else happening in two-way? So let's say in the case of multi-access network, when I have multiple routers, so when I said there will be election happening, DR and BDR, now that's happening over in this step. DR and BDR will be selected. And how do they select? How do they get selected? The formula is priority plus router ID. Okay. And the highest will win the election and it will be elected as DR. In the case of routing, it's the highest that is considered. Whereas in the case of switching, it was the lowest that we used to consider for STP election or any kind of thing. Okay. In the case of routing, it's always the highest that wins. So whoever has highest priority plus RID will take up the DR in case of multi-access. In the case of point to point, there will be no DR and BDR. In the case of this scenario, point to point, there will be no DR and BDR. DR and BDR happens only on multi-access. Okay. So that is why I call this as optional, because you never know, the OSPF might be establishing on a point to point. So don't expect there will be DR and BDR happening in such scenarios. So that's why I call it as optional. So DR and BDR is during multi-access. Now let's say neighborship are formed. They know, the two routers know who is connected to me and they have negotiated with all the parameters and they are good with that. Okay. So in the next step, okay, so as I was telling, we just completed the 3 states out of the 7. Okay. So in the next step, in the extract step, they are going to form master and slave relationship. Okay. They are going to find who is master and who is slave. Now why do master and slave is required? So now let's say I have 2 routers. Okay. R1 and R2, they have formed two-way neighborship. The next concern is who is going to share the database. Okay. So R1 is going to say I am the master. Okay. I am the master, and even R2 is going to say I am the master. So I am not going to share. So who is going to share in the case of in this case, who is going to share? So basically there will be a negotiation happening. So one of them will become master and the other one will become slave. Now the formula for that is so let's say formula to find master is priority what do you say router ID. Okay. So the highest will win the election. So the router which have the highest router ID. So let's say I have 1.1.1.1 and I have 2.2.2.2 as a router ID. Now this one will become master and this one will become slave. So what master says is, so master is going to share the database. Okay, now R2 is going to share the database. Now this is going to say I have 5 different networks or I have 4 different networks. So it's going to send the copy of 4 networks. It's not going to say what are the 4 or 5 network. It's just going to send the copy of there. Okay. Now that's in the exchanges. What is happening in extract? They're selecting master and slave. In the exchange, they are going to share the number of networks. In the loading, they are going to share the copy or let's say it's going to share the actual neighborship or actual network. So R1 or R2, they're going to share the individual networks 1.1.1, 2.2.2, 3.3.3. Okay, and full is a state where both the router will have consistency database. So let's say it has 10 networks. Now the whole thing will be also replicated on router 2. Okay, so these are the 7 steps which happens in the case of OSPF. So I'll just write once again. I know it's little confusing. Okay. So I guess it was clear till down in it 2-way. In the case of extract, exchange, loading, and full. Okay. So as I told you, both the routers R1 and R2 decide or they form neighborship, and in the case of multi-access they form DR and BDR. Okay, now the confusion is who is going to share first. Share what? The database table, DBT, database table or database descriptor. Okay, so R1 say I'm the master, I'm going to share. R2 says I'm the master, I'm going to share. Now the formula for master is router ID. So one with highest router ID will win the election. So let's say this wins the election. This becomes master. Now R2 is going to share the database packet. Okay, in this step, saying I have 5 networks with me. Okay, and now R1 will send after that. After receiving the packet from R2, R1 will send saying that I know 10 networks. So let's say it has 10 networks and R2 had 5 networks. Okay, so they are both going to talk now. They're both going to tell I have so and so network, I have so and so network. Okay, the actual exchange has not happened. They are not going to share who is or what is the content, or they are not going to share what is the content at this point. Okay, so something like, let's say you have 2 neighbors. So the neighbor 1 talks about the family members, but they are not going to share who is doing or who is working where, what is their name, or what is their day-to-day activities. They're just talking about their strength, that I have 5 family members at my home. The other person says I have 10 family members at my home. They're not exchanging the actual information. So the actual information will be exchanged in the loading state. Okay, so the actual exchange will happen in the loading state. Okay, and then once they both synchronize, that is now 10 plus 5, router 1 knows about 15 networks altogether, 10 and 5. Similar way, router 2 knows 10 and 5, 15 network, both are having the same database now. Now they achieve adjacency. Okay, so this is a state when they have formed the neighborship, they have exchanged the database, and they know about each and every network. Okay, that's when you reach full state or adjacency state. So now there is one slide in a small interview question. So let's say if someone asks you, when do you call neighborship in OSPF? Okay, It's not when you have full state. Okay, full is called as adjacency. Neighborship is achieved in two-way state itself. Okay, even though you have not exchanged, okay, even though you have not gone through the step number 4, 5, 6, 7, you still are neighbor. Okay, to form neighbor, I just told you there are router ID, and along with router ID you are sending the 5 or 6 components. Now that should match to form the neighborship. Okay, so we will do the lab over on this. It will be more useful rather than the explanation. Okay, so you have down state, you have init state, you have two-way state, extract, exchange, loading, and full. Okay, fine. Now let me go back to the topic which I had skipped. Now regarding to the packet type. Okay, so as we discussed about 7 state, that is down, init, two-way, extract, exchange, loading, and full. Now there are some packet which are responsible for these steps. Okay, so your hello packet is responsible for first 3 steps. Okay, and what is the component of hello? So basically hello packet will take router ID, and along with router ID it's going to take 5 or 6 different components like the hello timer, dead timer, authentication, area types, area ID, okay, subnet mask. So these are the component. Whole together we call it as hello packet. Okay, so this hello packet is seen across in the first 3 steps, not in the down state. Down is when you have not enabled. Okay, I'm just considering when talking about the 7 steps. Okay, the first 3 will be hello packet. Now in the case of so do you guys can hear me? So do you guys can hear me, or okay, what about now? Is it fine? Okay, okay. Now what is the next packet? That is database description, or DPD or DDP. Okay, now that's over here. Database descriptor. Now that is the packet which is taking care of extract, exchange, loading, full. Okay, now where is LSR, LSU, LSA, or I can also write LS. Okay, now where is these packets seen? Now these packets are seen, or these packets are seen in your day-to-day OSPF environment. So let's say I have couple of routers. Okay, they have formed the neighborship, they have gone through the full adjacency. Okay, now addition or deletion will be sent over update packet. Okay, now this update packet is called as link state update packet. Okay, it's called as link state update packet. Now let's say there is a let's say this router. Okay, now let's say this router is asking for an update. So let's say it has a network of 1.1.1. Now this will send a packet called as link state request to get an information about 1.1.1. Okay, and now that information will be sent over on link state update, and now after that it's going to send ls acknowledge saying yes, I have received this. Okay, so you can also make use of LSR, LSU, LSA in this scenario as well. Okay, So let's say in the case of extract and exchange, it's making use of database description packet to exchange the database. Okay. In the case of loading, as I told you, in the case of loading, it's going to send a LSR packet asking for more update, and that update will be sent by LSU, and then it will reply back with acknowledge packet. Okay. So there are three things happening here in the case of loading or in the case of exchange. So let me tell you what exactly is happening in exchange and loading. Okay. So in the case of exchange, okay, so let's say in case of extract, they have elected who is master and who is slave. Now in the case of exchange, the master is going to send a copy, just a copy, or I can just say it's a summary of the network that router has. Okay. In the case of routing, sorry, not routing, in the case of loading, now what happens is they know what is the number of network or what is the copy of each other's network or each other's router. Now they are going to request more information. Now there is way you will send LSR asking for more update on this network. Okay. And your second router will update you with LSU, link state update, saying 1.1.1 has a prefix length of 24, it has a destination of so and so, it has a metric of so and so, and all other things will be sent. And now the first router will say thank you with the acknowledge packet, LSA packet, and then they reach to the full or agency state. Now here is where you will see the OSPF packet, OSPF hello packet, OSPF DPD packet, and the other link state packet. Okay, so you have 5 different packet in the case of OSPF. Okay, so this is about the hello packet. Okay, it should have been hello packet. As I told you, what is the what is hello packet consisting of? It will consist of router ID and all these different parameters: authentication, area ID, subnet mask, priority, intervals. Okay, hello and dead interval. Designated and backup designated will be elected up in two-way state. Okay, and the active neighbor. So these are something which is the component of hello packets. Okay, now regarding router ID, now this is very important. Okay, why do I say this is important? Now let's say you have one router. Okay, a brand new router. Just log into this router, go to the configuration T, and just try to enable router OSPF process ID. You will never have the OSPF process coming in, or you will never see the process coming up. The reason is there is no IP address that is assigned to any interface, or you do not have any IP address on any loopback, neither you have a manual router ID, and that is why your OSPF is not coming in. Okay, so to have your OSPF coming up, you must always have a router ID configured. Okay, now that's your basic building block for your hello packet, right? So what is your hello packet consisting of? It's consisting of router ID. Now if you don't take care of router ID, how is OSPF process going to come up? So while bringing up OSPF process, make sure you have a router ID, so that this router ID becomes or be a part of the hello packet, which will be sent to the second router. Okay, so how is router ID formed? So there are 3 steps, or there are 3 ways we can form router ID. The first way is manual. So I can go to router OSPF, and then I can manually mention the command router ID and whatever ID I just want to give it. Okay, now let's say I have not done this step. Okay, the second step here, or the second way to bring up router ID would be highest loopback interface will win the election. So let's say from a router point of view, I don't take care, or I don't manually configure, but still I have some loopback with me. Let's say loopback 10, loopback 11, loopback 20. Now the highest loopback address, let's say that's having 20.20.20. Now this will be automatically acting as a router ID in the case of OSPF. Okay. Now let's say you don't have loopback as well. Okay. Now third tiebreaker here would be the highest physical IP interface. Okay. So let's say you have F0/0 with some IP 1.1.1.1. You have F0/1 with 2.2.2.2 and so on. Now the highest one will take up router ID. Now this is very important. If you don't have router ID, your OSPF will never come up. Okay. So you must get the router ID up. And to get the router ID, you have various way to get them up. So you can configure manually. Let's say you don't have something manually configured, your loopback can be automatically considered as router ID. Let's say you don't have loopback, you have physical IP, the highest one will. Okay, so I guess I'm all good. Okay, so let me just see once again. We went through the OSPF key points, OSPF packet types, hello packets, the router ID, the 7 OSPF neighborship process. Okay. Yes, regarding designated and backup designated routers. Okay, as I told you, in the case of multi-access network. Okay, in the case of LAN, let's say when I have a switch and the switch is connected with multiple routers, and now you bring in OSPF. Okay, so in such scenarios, the broadcast will keep on increasing. Okay, as I told you, if let's say there is a update packet, now this packet will be sent to every active interface. Okay, now that will be taken to the routers, and now router will send another packet, acknowledge packet. Okay, now that packet will be once again taken to all other active interface. Now let's say the acknowledge from this router was also been sent to all other active. Okay, and so on. Now there is a lot of broadcast happening within this. To avoid such, or to minimize the broadcast packet, we are going with DR and BDR election. Now how is DR and BDR elected? It's your priority plus router ID. Okay, so by default the priority is 1. Router ID, you have 3 ways to get elected. One is manually configured, loopback, and highest IP address. The one with highest output will be considered as DR. Okay, and the next one will be considered as BDR. Why do we need BDR? Let's say all of a sudden the DR router, let's say this was a DR router and this goes down for some reason. Now what happens? You need a BDR which can act as DR immediately in the case of outage. So let's say this was BDR backup. Okay, now this one will be put up as DR in the absence of the main router. Okay, so now all the packets will be sent to this router and this router will acknowledge back. So that's where is this happening? Where is this election happening? It is happening in the two-way step. Okay, in the case of two-way, the DR and BDR will be elected. DR, the formula is priority plus router ID. So priority by default is 1. In the case of OSPF, yes, you can tune it. You can have between 0 to 255. Okay, now router with 0 will never participate on DR and BDR. Let's say on routers, let's say this router, which is 1800 router. Okay, you don't want this router by mistakenly taking up DR and BDR. So what you can do is you can turn off the election by setting up priority 0. So if you set priority 0, then they will not form, or they will never negotiate for DR and BDR establishment. Okay, That scenario when, let's say, you have all better routers, like you have some better router like 2800, 2800, 2800, and one of them is 1800, or very very outdated router like 800, just a simple router. Now you don't want this router to become DR or BTR. Okay, so in that case you can turn off the election by setting up zero priority. So anything from 1 to 255 you can play around, you can change the behavior. The one, let's say you want to make this as DR, you can change around with the priority and you can make this. Okay, and router ID, as you know, there are 3 steps. Okay, and this diagram is about the multi-access network. Why do we need DR and BDR? Okay, so let's say I have a switch connected with 4 different routers. So if you just see, they are actually forming the neighborship. Now there are 6 neighbors here: 1, 2, 3, 4, 5, 6. Okay, 4 routers. When they are in a multi-access, they are forming 6 neighborship. Now let's say you had 100 of them. You had 100 of them. So how many neighbors are they going to form? So the formula is here. Okay, so if you have 100, 100 minus 1 divided by 2. Now that's 100 into 99 by 2. Okay, so you can just see how many neighbors are they going to form. So the more neighbors they form, your unwanted packets or your unwanted broadcast will be keep on increasing. Okay, and to restrict that, we make use of DR and BDR concept. Now what happens? All your other routers will discard the packet. Okay, it's only your DR and BDR which are listening on 224.0.0.6 which will listen to the updated packet, and they will synchronize, and then okay, so in the case of DR-BDR which are listening on 224.0.0.6, they will listen on the update packet, they will synchronize, and now they will send back the so in the case of DR-BDR, the DR will send on 224.0.0.5, and which is where your all other routers which are called as DR others. Okay, all other router which are not neither DR neither BDR, the other ones are called as DR others. Now they are listening on this multicast type. Okay, so this is when you have multi-access type of topologies. Okay, and this is the exponential increment when you have the router. So when you have only 2 or 3 or 4 routers, you can see so many broadcasts happening. The more number of routers you get in multi-access, the broadcast will also increase gradually. Okay, because of the formulae. Okay, so the more number of routers you have in multi-access, the broadcast will increase. So you need to take care of this. Okay, by having the DR. Okay, so in DR we have something called pseudo node virtual router. So basically DR is nothing but they are acting as a virtual okay, so let me tell you what is pseudo node. Okay, so let's say I have this switch, I have couple of routers. Let's say this is elected as DR. Now what is DR? Basically DR is basically acting as a virtual router to each one of them. Okay, so this is going to send update to DR, then DR will distribute. Let's say there was some update here, it's going to send to DR, DR will now update to all others. Okay, so DR is acting as a virtual gateway, like pseudo node virtual router. Okay, so all the rest, they will not communicate to each other. They are going to discard those packets. Even if they are going to send some packet to each other bypassing DR, they will be discarded. In DR BDR, it's always with respect to DR, and then DR will take care of distributing. Okay, so if DR is down for some reason, you have the backup designated router which will act as a DR. Okay, So this is a simple overview of the same thing. In the case of multi-access, let's say I have a switch here. So your DR will send the multicast packet on 2240.0.6. Okay, multicast packet to BDR and DR. Now DR will send a unicast packet. It's going to send a unicast packet to that router. Okay, and then it is going to distribute those packets to all other routers, and all other routers are going to update their database. And that's how, let's say if DR know 50 networks, now those 50 network will be also learned on all other routers. Okay, so I'm talking about multi-access topology. Okay, in the case of point to point, what is point to point? When routers are straight away connected. Let's say this way. This is a point to point network. Okay, so let's say this. Now in this case, I don't need DR and BDR. Okay, I don't need DR and BDR. There is no broadcast happening in this scenarios. So in this scenarios, there will be no DR and BDR. It's only when you have the multi-access, the switch which is connecting to multiple different networks. Okay, and altogether, if you just combine, they just form something like this. So let's say this is a multi-access network. Okay, if you just see from this point of view, they are forming actually 6 neighborship, 4 routers, but they are forming 6 neighborship. They are exchanging the database. Okay, the switch is broadcasting every time, which is increasing the broadcast in the network. Okay, now regarding the OSPF configuration, there are 2 ways we can configure OSPF configuration. One is by global method. You go to config T and bring in the configuration, and that's going to bring up the OSPF process. So regarding the configuration, there are 2 ways. One is global way and the second one is interface way. Okay, so that means the first one is you go to configuration T, you go under router OSPF and you define the network and you bring up the OSPF process. The second way is you go directly within the interface. Okay, and then you bring up the OSPF process. The problem with this is, the problem with interface type of configuration is, let's say you have any other configuration, like you have BFT configuration, or let's say you have HSRP configuration, or any other interface related configuration. Now in that scenario, what happens is your OSPF will have some issues. Okay, so I'll tell you what kind of issues. So for such scenarios, the centralized configuration is preferred. Okay, so when you go towards router OSPF and you configure, it's called as centralized. Okay, centralized way of configuring OSPF, and this is called as interface specific configuration. So we'll discuss each one of them. So in the case of network centralized option, you just go to the OSPF process, you will define the area, you will define the network statement, and you will just bring in. Okay, now there is misconception saying, okay, so what some people have a misconception. So some people say that router OSPF, let's say 100 or whatever. Now if I write network statement, let's say 192.168.1.0 and the wildcard mask and the area. Now some people think that this is actually bringing up the OSPF process. Okay, now that's something you should know, that just having this will not bring up, or it will not start working the way it should work. Okay, you need to define your interface also later on. You go to interface FA0/0 and then you have to include this IP address. Let's say now I configure this interface with IP address 192.168.1.1 and 255.255. Now that is how this interface will get mapped with this centralized OSPF process, and now this will start sending up the hello packets or the OSPF packets. Okay, so without this, it's only that you're going to get the OSPF process, but they are not functional. It will be just within the router itself. Who is taking out? It's your interface, and you have to bring in the interface configuration. Now if you guys are thinking, if that is the case, then how is it different than the second point, right? So in the second point, you don't configure this. Okay, in the second point, you don't configure this. You go to interface, you go and configure IP address, and then you add IP OSPF configuration straight away within this. Okay, that's an example for the second type. Both are different. Okay, in case of centralized, you have to bring up the OSPF process, and then you have to define the interface, or you can say you have to map the interface which will take out those OSPF packet, or it will receive the OSPF packet. Okay, so that's whole together the configuration for the first one. And for the second one, you just go to interface, bring up the OSPF process, define the IP address. Okay, and that's a configuration for interface based. The concept is similar to EIGRP, except the OSPF area fact. Okay, this is the centralized way to configure OSPF. You go to router OSPF, you configure different networks. Okay, and this is something which we see in the case of OSPF only. In the case of EIGRP, we don't see concept of areas. Okay, and yes, OSPF will also support the secondary IP address. In the case of EIGRP, they don't support secondary IP address, but in the case of OSPF, it's going to support secondary IP address. Now, regarding the second type of OSPF configuration, that is interface specific configuration, let me show you the configuration straight away. Okay, so you go to interface, you will define the IP address, and you will define the area which this interface belongs to, and there is where they will start sending the hello packet. They will start sending or receiving the DPD packet or LSR packet or LSU packet. Okay, so two types to configure the OSPF. Now this has some drawback. Okay, so the drawback is, if it's a hybrid configuration, that means if this interface is also part of some other configuration like HSRP, BFD, or any other thing. So now what happens is, your network statement and so what happens is, the drawback of having interface specific OSPF configuration is, when you have some other protocol enabled, the settings will take decision. Okay, now let's say under 0/1, you are defining hello packets, a customized hello packet, or you have a metric defined. Now now those configuration will start overlapping with other configurations. Okay, so that's why keeping OSPF on a centralized basis and keeping interface are two different things. Okay, so depends on network. Most of the time it will be centralized, but yes, you can make use of interface bases also. They are faster. Okay, this is very faster. You just have to give one extra command. That's all. You just have to define IP address, which you would be doing, and then just define one single command. In the case of here, you have to make use of the wildcard mask, the areas. Okay, which you don't have in such scenarios. Okay, now regarding passive interfaces. So this is a scenario where, let's say I have a router with multiple interfaces. Okay, I have 192 network, I have 172 network, I have 10 network, let's say I have 192.16 or 168 network, and I have 1.1.1 network. Now I need my OSPF packet to be taken out and also received over here. Okay, but on this interface I don't want any OSPF neighborship. Okay, neighborship in the sense, let's say on other side, let's say they are forming neighborship. Okay, so there is a OSPF neighborship here. Similar way there is a OSPF neighborship here. Similar way there is a OSPF neighborship here. So as the same thing over here. Now you don't need any kind of OSPF neighborship between these two routers, but at the same time you just want to advertise 1.1.1.1 inside routing, okay, or inside the database. You want this to be part of the database packet, but you don't want any OSPF packet to be in and out on this interface. Okay, because you don't need any kind of OSPF neighborship between these two. Okay, so in that case what you can do is you can passive this interface. So the moment you passive this interface, it's going to stop those packets. Okay, so which kind of packets? It's going to stop the hello packet. There will be no hello packet sent, and even if you receive any sorts of OSPF packet on that interface, it will not be processed. Okay, so that's the meaning of passive interface. So it's to limit the OSPF hello packet and processing. Okay, you just don't need the OSPF process to be activated on all the interfaces, so you can just bring down few of them. So one method was just go on the routing process or the router OSPF process and just configure the passive interface. Okay, something like this. You can passive that interface, or you can passive the whole or all the interfaces by this command, passive interface default. This will bring okay. So as I told you regarding the OSPF neighborship, so these are the parameters to form the neighbor agency. Okay, so there should be router ID. Without router ID there will be no OSPF process coming in. Once router ID has been configured, or by default router ID is picked up, then they must have the common subnet. Okay, then yeah, the common subnet is nothing but network mask. They must have the common area ID. They must have DR. They must have hello and dead timers. They should have the same authentication, and they should have the similar area type. Okay, now regarding MTU, they can still form two-way. Okay, but they will not form agency. This we will do in the lab. I'll show you what does it mean, and very what do you say, from technical or from interview point of view, you can expect this question. Okay, if a interview asks you that we see that two-way has been achieved but agency is not been formed, now tell me what could be the troubleshooting steps, or what would be the issues here. So you should know from interview point of view as well, because there are a lot of scenarios that can be asked here. Okay, so this will be taken up in the lab. In the next class I will do lab on each and every parameters when there is a MTU mismatch. So as I was telling, I will take lab on each and every points here, like if there is MTU mismatch, what happens, how is area ID to be matched, how is router ID elected, how is the hello timer or manipulating the hello timers will bring down the neighborship. Okay, so this will be part of the lab. I'll show it. These are the configuration of OSPF. Okay, so you have all OSPF. I mean, you have the interface configured, and then you have router OSPF configured. This is a centralized method. Okay. How do you passive any interface? Just one single command. It will passive that. Okay. Confirmation of interfaces. I think I will better take this tomorrow. Okay. So nothing much here, nothing much here. It's something which, okay, let me show you here. So let's take one or two routers. I'll just show you how do we configure OSPF. Okay. So let's say I have first router and I have second router. Now what is this an example for? This is a multi-access example for multi-access. Okay, there is a switch here, and the reason why I took this is so that I can show you the DR and BDR election. Okay, in case of point to point, like in this scenario, in this scenario, which is point to point, there will be no DR and BDR happening. Okay, in the case of multi-access, there will be DR and BDR election. Okay, so we will see this in the next class. We will see how the DR BDR happens, but quickly let me show you one of the OSPF lab. Okay, so how do we configure OSPF? OSPF process ID. Now this process ID should what do you say, it's a locally available. They don't have to be matched. Okay, the process ID that we configure is for internal use. In the case of EIGRP, we were making use of autonomous system, and this autonomous system had to be the same on two routers. Okay, so if I have two routers, R1 and R2, they must have a unique autonomous system to form neighborship. But in the case of OSPF, this is just internal. That means you can have process ID of 100 on one side, and on other side you can have process ID of 200. Now they don't have to be matched up, but yes, later on there are some configuration like area 0, area 0. Now that should be important. Along with that, you have other 4 to 5 parameters which should be same. Okay, I know it will be little confusing. Do practice. Only practice will help you to come out of these confusions. Okay, between EIGRP and OSPF. Okay, let me configure this router OSPF 100 network. So what is the error that I got? I got an error saying OSPF process failed to allocate any router ID and cannot start. That means I don't have any IP address configured. So if you see my IP address, show IP in brief, I don't have anything. Okay, neither I have any loopback address. Neither I configured any router ID manually. So that's why my OSPF is not coming up. Okay. So what can I do is I can just configure a manual router ID. Okay, with 1.1.1, and I can give some networks. So I can just give all the networks with important command area 0. It says that this router is a part of area 0. Okay. Now let me go to the interface here is E0/0, and what is the IP address of that? Let's give it as 1.1.1. okay, not 1.1. Let's give it as 192.168.32.1 255.255.255.0. no shutdown. Okay, now I'll go to the second router. I'll configure router OSPF, now let's say 200. Okay, so I have 100 here, I have 200 here. Just to prove they don't have to be the same, they don't have to be matched. You get the same error, ignore this because you're going to configure router ID. So you can make use of 2.2.2. You can make use of the whole network. You can configure area 0. Now go to interface 0/0. Configure IP address 192.168. what is the IP that you gave here? 32.2.255.255.255.0. no shutdown. Okay, so if I just take up capture, so you will see there are some OSPF packet that's coming in from 32.1. Okay, so your OSPF process or packet are coming from this toward this. Okay, as of now it's coming over here. The reason is you have not configured this, so there is no packet going on other direction. Okay, so what I am going to do, I'll just go and make it no shutdown. So as soon as I do no shutdown, I can see the packet will be started up from 32.2 as well. Okay, and they will immediately form neighborship. So you can see it formed neighborship. Okay, what are the things happening here? There were hello packets, hello packet, then the DB packet, LSR, LSU, and LS acknowledge packet. Okay, so what are these? These are the 7 steps. Okay, if you just recall the 7 steps, that is down, init, two-way. Okay, so while discussing about these 3 steps, so while discussing the first 3 steps, it was all these packet, the hello packet. Okay, not in the case of down, but since it's a part of the 7th step, I'm counting it. Down is a state when it's not processing any hello packet. Okay, just to consider it, I'm considering. If you ignore, yes, you can ignore. Okay, so hello packet in the case of init and two-way, once they form neighbor, once both the router know what is what, and they match the criterias within hello packet, then they go towards extract, exchange. What do you have next? You have loading and full. Okay, so over here there will be master and slave, which will be happening with the help of this packet. Okay, DBD packet, database description packet. In the extract and in the loading, it will be LSR, LSU, and LS acknowledge. Okay, the rest of packets that you see here, so those packets will be taking care of the remaining stages here, and then the 2 routers will have the equal number of neighborship and the networks. Okay, so let's say this is aware of 5 network, these are aware of 10 network. Now at the end of full, they will also know who is who. Okay, so basically these 5 will be known to this, which becomes 15, and the 10 over here will be known across to this. So basically there will be 15 network that both the router can learn. They understand how is these network connected. Okay, so these are the packet behind the OSPF process which is taking care. Now if I open up hello packet, okay, and if I talk about those components that's consisting these hello packets, so you can see there should be subnet mask, there will be a interval, there will be dead interval. Okay, as you know, the OSPF priority by default is 1. Okay, so there is a designated router, the backup designated router is 0.0.0. Okay, and what else do we see here? So you see there are no authentication as of now, and under this, under flag, okay, under option, you will see the area types. There is no nothing configured for area type. So basically all your hello parameters, the 5 to 6 parameters of hello will be taken up in the initial phase of neighborship. Okay, when they are, let's say, 2 routers which are down and down. Okay, as soon as you bring up OSPF, what is OSPF looking for? It's looking for router ID. Once it gets an router ID, it's ready to send the hello packet. So the content of hello packet would be router ID, and along with router ID 5 to 6 hello components like the hello and dead interval, the authentication, subnet mask, and all other things. And this will be taken up to the router 2. Okay. Now let's say this also comes up with OSPF process. Okay. And as soon as it receives a hello packet with some router ID of the first one, which is 1.1.1.1. Okay. Now this the first packet would be multicast. Okay, on 2240.0.5. As soon as you bring up OSPF, you will have this IP listening on the hello packet. Okay, it receives a hello packet. Okay, and now it will send a unicast packet back to 1.1.1. Now that would be a unicast packet. And now what is it going to consist of? It's going to consist of its own router ID, which is 2.2.2.2, along with these hello packet parameters, also the router ID of the first one. Okay, now the whole together, this is received on the first router. First router will get converted to 2-way because it can see the incoming hello packet has the router ID of the first one along with the router ID of second one. Now it's good to okay, looks like there was a small voice drop somewhere. Okay, so as I was telling, so as soon as it receives a hello packet with router ID of R2 and its own router ID R1, it gets converted to 2-way. Okay, and it's going to send a hello packet with its own router ID and router ID of R2 to the second person. And now it see that it has the hello packet, the incoming hello packet has a router ID of R2 as well as R1. Now it also get converted to 2-way. Both of them form neighborship. They are just forming neighborship. Okay, the database are not synchronized yet. They are forming neighborship. They are making sure who is DR, who is BDR, and then they follow the next particular process of the other things where they share their database. Okay, so first they will elect master and slave, then they will send the database, the copy of database. Okay, I say it as copy or header of the database. They are not going to send the complete database, just a copy or header. Later on, the LSR packet, LSU packet will be used to pull the information. R1 will say, I need information of this network. Okay, and then the second router is going to update back with LSU packet, and the first router will send acknowledge packet saying yes, I have all the information, I am good with this. Okay, and that's how they achieve the complete agency in the case of OSPF. Okay, so as of now, it's better we wind up. Okay, I know there are a lot of topics which we discussed, so if you get time, go back and just go back to this notes which I'll put up on the website. Okay, so be prepared for the next class. In the next class we will do practical where I will try to uh, break through some the parameters. I will break the hello timer, I'll break the M2 packet, I'll break lot of things, and we will see why the neighborship went down, why it was important. Okay, so in order to understand that, it's better you know what is the theory behind that. Okay, so if you don't know theory, making any changes in the lab will not be useful. Okay, so fine, so I'll wind up for now. Let me know if you have any doubts. And one more thing, since I lost my screen, okay, I also lost all the previous text which was put up here. So instead of seeing unused interface with no IP is a great way to see exactly what interface are assigned to your interface. Okay, LSA type not part. Yes, it's a part. It's a it will be included. Don't worry. Okay, it will be included in NRC or might be after 1 or 2 classes. It will be. Unicast is not 255, it is a direct point to point. Okay, so in case of unicast, basically the router 2 knows how to reach router 1. Okay, so how is unicast acting? So in the case of unicast, so it knows this is the IP of router 1. Okay, so it knows how to reach there. So it will directly send over on the IP basis, not on multicast or multicast IP. Yeah, LSAs are included. Okay, yeah, that's true. It is included. So basically, today what we covered is to get started with OSPF, the basics of OSPF. In the next coming up topic, we have LSA type, we have stub, we have virtual link, summarization, we have filtering. Okay, so a lot of things are included in OSPF. OSPF is a what do you say? There are a lot of theoretical topic and there are a lot of things in OSPF, whereas EIGRP was pretty straightforward. So the class we had today was a basic OSPF. Okay, regarding to the theoretical and all other things. So apart from that, we have a lot of other things as well, which is in the upcoming classes. So any doubt, please let me know. Okay, so secondary IP is when you, let's say I have a router. Okay, so this interface have a primary IP, and apart from primary I have couple of secondary. Okay, so the work of secondary IP is just to process the packet. Okay, so these secondary IP will have some IPs configured. Let's say 1.1.1. I have another secondary IP which is 2.2.2. Now let's say there is a packet which is going out. So the packet can be sourced from this secondary IP. Now let's say I need one packet which should be taken sourced via this IP. Okay. Now the source will be 1.1.1.1 and destination is whatever it's going across to. Let's say I want another traffic where the source to be put up as 2.2.2. Now in this case the source header will be changed to 2.2.2. Okay. It's when you are having multiple different networks, or I can say you have multiple different users connected on over on this network. Okay, so each network will have the gateway, or I can say that the traffic has to be sourced accordingly. So in that cases you can have multiple IPs. Okay, regarding the classes, I'm not sure until we are good with OSPF. So might be 3 4 classes or 1 week. I'm not pretty sure. Okay. Yeah, they are little complicated, but don't worry. The lab or practical will make it look simpler. Okay. Okay. Regarding the description and interface label, there are some option. Let me show you. So you have these options which you can make use of. So you can see the labels. Okay. But yes, if you want to see the whole topology, then this will not work. So let's say you're making use of part by part, then just go towards that part and just get it up. Okay, or keep something like this. Okay, so I guess there's no more doubt, and we are good to wind up. So let's meet up in the next class. Okay, so I'll pass on the document. Please go through once again. Okay, and if you have any doubt, do let me know. So till then, have a nice day, and we'll catch up in the next class. Okay, see you everyone.